Hello, welcome back to another episode of Stats with Mats. Today is a very, very momentous day in your life. This is a day that I imagine you will always remember for the rest of your life. The day you learned regression. Congratulations. The whole semester has been building to this. And in a way, your whole life has been building to this moment. Regression techniques, of which there are many, these are by far the most important sociological methods within our statistical toolkit. These are by orders of magnitude the most useful statistical techniques for the quantitative sociologist. And these are inferential models, statistical techniques that are proven to be in demand within the marketplace. If you learn these and if you get a bit of a level of comfort and familiarity with how to construct and interpret regression models, that can get you paid, really. Like this stuff can absolutely get you paid. So my goal for today is I'm going to start with a little bit of review. Where did we leave off last time with bivariate correlation? Because that's very much the lead in to bivariate regression. Then we will look at the regression equation, the regression line, and finish up with how to interpret coefficients in terms for actually calculating those coefficients. I'll be doing that the next time we have a full lesson. Okay. I don't really have, we're now 4 weeks in or three weeks in, 3.5 weeks in, whatever. And I'm running out of witty things to say about movies. So I will just say over the weekend, I watched Gone Girl and I enjoyed it. So that's my movie update for now. Anyway, let's start with our review. Bivariate correlation, we established tests for whether or not there is an association between two interval level variables. And it did so by using pairs of observations. The gist of bivariate correlation is trying to quantify what happens to y given a change in x. As x is increasing, does y also increase? Does it decrease? Does nothing happen at all? And we did so using the Pearson's product movement coefficient. So r equals n times the summation of xy minus the summation of x times the summation of y divided by the square root of n over the summation of x squared minus summation of x squared times n times the summation of y squared minus the summation of y squared, which we then, using degrees of freedom and the probability or the probability of rejecting the null of 0.5 or 0.1, we're able to calculate a number that was between -1 and 1 on the extremes. And that allowed us to evaluate three things. Pearson's product movement coefficient is very helpful for understanding the direction of the relationship and the strength of the relationship. But it does not tell you the magnitude or the units that are being used within this relationship. And it's limited to 2 and only 2 variables. It is those 2 flaws that regression is designed to address. Okay, so regression. What is the magnitude of the effect? Okay, well, we can say whether it's a strong or a weak effect, but here's what I mean by magnitude. Pearson's product movement coefficient will tell you, let's say, as years of education increases, there is a strong effect, a positive effect on the income that one makes in a given year, let's say. And so we can see whether that's a positive or negative relationship and whether that's a strong or a weak relationship. But let's talk more specific numbers than that. Correlation does not tell you for every additional year of schooling you obtain, how much more money can you expect to be earning on average? That's a powerful, powerful technique to use for estimating the magnitude of effects, okay? And we can also express it in units. Pearson's product movement coefficient is unitless. It's between -1 and 1, and it always will be, no matter what the units of the variables you're correlating are. But what regression will tell me, to use that one example again, what is the specific dollar effect given a 1-year increase in education, something like that. That's a very powerful technique to be able to use. So here's what regression does. Bivariate regression is going to estimate the change in y, that's your dependent variable, given a 1-unit change in x, that is your independent variable. And it will express it in the units of y, the dependent variable. Now, once we go through x's and y's and the rest of the equation here, my hope is that will make more sense. For now, all I need you to keep in your head, all I need you to really keep in your mind is what is being added through a regression equation. It is the magnitude of the effect, and it is the units of measurement. And that helps you really describe society in the language of mathematics very, very powerfully. Any questions? Hope. Okay, so let's move on. Remember our old friend, the line of best fit? Well, it turns out that that has a second name that it goes by. The line of best fit that we put through a scatter plot of two interval level variables, that is also known and called, that is also called a regression line. A regression line is trying to fit, remember, it's trying to estimate what is the general trend through the data that minimizes error within the prediction? What is the line that balances out the error above the line and below the line? The deviation from the line of best fit per data point should always sum out to 0, because positives and negatives will cancel each other out. But because the line is rarely flat, that would be no effect. The severity of the slope that you see here, that's also estimating, that's also standing in for the magnitude of the effect. Now, we didn't really quantify that when we did correlation. Now we're going to actually estimate and quantify that. The slope coefficient of a line is the regression coefficient. What that is doing, it is providing an estimate of something you may remember if you took linear algebra at some point in your career. It's an estimate of delta x on delta y. What does delta mean? The Greek letter delta there, let that stand in for change in x on change in y. What is the effect on y given a change in x? That's the slope coefficient, and that is going to be what we interpret when it comes time to actually put this in the language of social relationships. And the equation we are going to be focused on here is as follows. The regression equation is identical to what you always learned back in the day as the equation for drawing a line on an XY axis. So here's the point where I try to trash some of the crap that you learned back in the day. Please raise your hand if you learned that the equation for a line is y equals mx plus b. Okay, now forget that. That is wrong. I will hear nothing of it. If you write y equals mx plus b, I will fail you, and there will be no discussion over the matter. The correct line equation for a line is y equals bx plus a. Okay, I'm not going to fail you. It's going to be okay. But just understand that social scientists generally use y equals bx plus a, whereas in like algebra, for example, it's often taught as y equals mx plus b. It's the same thing. It's the exact same thing. But for now, because I will be using b as the slope coefficient, understand that that will always be conceptualized and used in an equation of y equals bx plus a. So what are the components of the equation here? We have 4 letters all corresponding to something different. Y, will be the value of the dependent variable, the thing that's being affected by something else. And if y is the dependent variable, I think you see where this is going. What is x? X, let x stand for the value of the independent variable, the thing that is doing the affecting on something else. So what we are trying to figure out, right, the slope coefficient is the regression coefficient. What we're going to calculate is the magnitude of the effect of x on y, the magnitude of the effect of the independent variable on the dependent variable. So then as far as A and B is going to be the slope coefficient. It measures that's a measurement of how steep or mild the change in the line is. Like a very steep line will have a large value for B. A very flat line will have a very small value of B. And that leaves only A, which you may remember, this is going to stand in for the y-intercept. The y-intercept is, I'll get into this at a later point, but the y-intercept is very simply the value of y when all predictors equal 0. What is the value of y when x equals 0? Okay, so let's go through that one more time. Let y stand in for the dependent variable. Let x represent the independent variable. Let b be the slope coefficient, and let A be the y-intercept of the line, the point where it crosses the y-axis. Okay, how are we doing so far? Doing okay? This is the point where I wish I had you guys in front of me, really. I wish I could do this in person because I could kind of see if people were if this was jogging your memory from like high school algebra or something. Something else we have to add to this. With any regression equation, keep in mind, we're using sample data to predict population data. So X is rarely, if ever, going to perfectly predict Y. What about all those pesky error measurements I kept talking about with correlation? So let's add E to the equation here. So now the equation for a predicted line is y equals bx plus a plus e, where again, y is the value of the dependent variable, x is the independent variable, b is the slope coefficient, a is the y-intercept, and e will be the error term. The error term is very simply the cumulative error of estimation that captures all remaining variation in y that cannot be attributed to the movement in x. What that means, I guess, a little more intuitively, is for all of the potential variation in values of y, some amount of it will be predicted by x, and other elements of the variation will just be noise. It will be just stuff that's in the data. And so E will suck out that remaining variation. It's almost like you had a vacuum cleaner that only picked up specific things. Or think about it like a water filtration system that allows the water to pass through while trapping all the crap that might get you sick and get in your stomach. What the error term is everything else that's left behind that cannot be attributed to the movement in X. You may remember this term of y hat. We went over that with the when did we do that? Central limit theorem. It's the difference between an observed value and a predicted value. So y hat and y, the difference between that is captured by E, the error term. It is the piece of the variation that cannot be attributed to movement in X. Okay. Now, as for A, let's go over the y-intercept here briefly, although I already kind of did this. The y-intercept, or A, represents the place where the line crosses the y-axis. More intuitively, if you set x equal to 0, then what happens to B? Well, what happens to anything when you multiply it by 0? It becomes 0. So by doing that, by setting x equal to 0, you are only left with y equals a. So the value of y when x equals 0, it's the place, because again, if x equals 0, it cannot be sliding up this x-axis down here. It must be right here at the interplay of 0, 0. Therefore, the y-intercept acts as a baseline because we're going to be quantifying everything given a 1 unit change in X. So it's like, what are you moving up from? A 1 unit change in X is associated with a B unit change in Y. As this goes forward, it's got to be coming from somewhere. In this case, the y-intercept is 2, right? If you just look at this graph that I have here. So when x equals 0, y equals 2. Any subsequent increases in x are associated with increases in y that start from this baseline of 2. Make sense? Now, as for B, the slope, or what's known as the beta coefficient, let B equal stand for beta here. What that is estimating here, once you've quantified E and A, B estimates the average change in Y, the average change in Y, pardon me, associated with a 1 unit change in X. And because it cannot be a perfect estimate unless y is a perfect function of x, which it rarely is in real data, I can construct an equation right now very simply that where values of x will perfectly predict values of y, but that is not likely to be observed in real data. You just don't see that in the real complicated, messy social world like ever. So hence you have to pair the error term with it. This B term, the beta term, is also going to be known as the regression coefficient. It is the thing that you will be expected for interpreting. You're going to need to know what A is and what E is, but B is really what you're interpreting because that's what is happening to Y, given that change in X. Okay, so let's take stock here. What we're doing is something known as OLS regression. OLS stands for ordinary least squares regression. That right there should tell you that we're going to be taking advantage of the squared property again. Y equals bx plus a plus e. This is the simplest method that we know of for calculating the unknowns in the above equation. Now, what are the unknowns? Well, A, B, and E are the unknowns. In order to do this, you have to be given a data set, obviously. So you have to know what X is and you have to know what Y is. And using that, you can calculate a line of best fit with predicted values of A, B, and E. Those are the things that are being estimated by the coefficient. So it's really not any more complicated than that. It's just all statistical regression is doing here is taking advantage of some algebraic properties of the equation you already know to express a line. We want to know what is the effect on y given a change in x. Or put in the language of society, what is the effect on income given a change in someone's education? The usefulness of this for sociologists should be very, very obvious to you, I think, at this point. So what you're seeing here is 2 independent examples of OLS regression. What's happening here? Let's look at the equation on the left. The first line is a perfect fit between the data and the line that's drawn through that. Therefore, there is no error term that you need to actually put there, right? There's no real error term that is necessary because here, y equals x plus 4. What is 4 there? 4 is A, or the y-intercept. And a 1 unit change in x appears to be associated with a 1 unit change in y. Therefore, B equals 1. And over on the right, notice how the equation is identical because the line is identical. even though the data is not. The errors here are perfectly averaging out to 0. So I still have a y-intercept of 4. I still have a beta coefficient of 1, but I don't even need an error term here because the movement in x is perfectly capturing the movement in y, even though the line is now drawn through an imperfect fit. Pretty interesting, I think, right? So regression is really, it's just incredibly versatile. It's a very versatile, and it's something that you can be very creative with if you get proficient with understanding regression techniques. But that's all OLS regression is doing. It's fitting the line of best fit and estimating the slope coefficient through a scatter plot. And that's it. Nothing more complicated than that. Okay, I'll stop there, let you catch your breath a little bit, and then we'll talk about some other issues with regression. Okay, so when we draw a regression line, and the one that you see here is not a good regression line, we're going to need some crazy techniques to be able to handle that type of data. The regression line, the fact that it's ordinary least squares means it's the lowest squared number you can obtain given the properties of x and y within the data. The regression line is drawn so that the error of estimates is minimized. In order for it to be a workable equation, you have to produce the smallest estimate of E you are capable of producing, and only the sum of squared property can do that. It must be what is known as blue. Blue here stands for, notice how I put that in capital letters and blue. That stands for the best linear unbiased estimate of the error term within the data. What does that mean? In English, best means it has the smallest error term. Linear means that there is no directional change here. It constantly goes in one direction throughout the entire data set. And it must be unbiased in that all non-random variation is captured. You have to account for all non-random variation. What does that mean in practice? It just means that the error term has to be comprehensive. It has to be accounting for everything that is not tied up in the estimate of x. An estimate just means you're estimating something. So really what you care about here is blue, B-L-U. Now, as for what that would look like graphically, the blues. The black line that you see here, that's a blue regression line. It is the best estimate through the data. It is linear, clearly, and it appears to be unbiased in that there's some values above the line and below the line, but it all kind of looks like it cancels out here. Like that looks visually pleasing to us. Now we could calculate that. We could certainly actually check this, but it's not really necessary for the exercise here. What I need you to understand is that the red line is not blue. It's actually red. But you can sort of see that because look, does that look like it's the best line you could draw through the data to minimize error above and below it? No, it looks like it's heavily skewed towards just a couple of data points, and therefore is not accurately representing what's really going on in this GPA, high school GPA and college GPA prediction. So a good regression coefficient is always going to be the best estimate, a linear estimate, and an unbiased estimate. Now, if your data is not linear and that's valid in the data, that's okay. There's nothing wrong with that. It's just you're not going to be able to use OLS, ordinary least squares regression. The real prize here, though, with that standard regression equation, x is a given. So you'll be given x. You will be given y, obviously, and E is created by estimating the difference in the mismatch, or the difference between y and predicted values of y. Where does y hat come from? Well, it comes from x. You're using values of x to predict values of y, and then y hat is never perfectly predictive of y, hence the error term. Here's what we really want. What sociologists care the most about is the beta coefficient, because that is the estimate of change here. Now, in order to do this well, in order to do this right, let's focus on what is needed for the interpretation. First, I'm going to need both variables. I must express this as a change in y given a change in x. Therefore, I must be referencing both variables in my interpretation. That's number one. Now, as for number two, I need the coefficient. I need to be mathematically representing what that change in y is given the movement in x. And finally, I need the direction. Is y associated with an increase, or is y associated with is y increasing, or is y decreasing given that change in x? And once I know to look for those three things, I can interpret any linear quantitative relationship that is spit out by the regression equation. And that's pretty darn cool. Okay? So I want you to get very comfortable with the following terminology. A 1 unit increase in x. We will always be leading with that. A 1 unit increase in x. Because the B coefficient is assuming the regression line equation is making an assumption of a 1 unit change in x. And it's what's the average change in y given that 1 unit change in x. Now, again, if this all seems really theoretical here, if we examine an example, I'm very hopeful that this will start to really crystallize for you guys. So, is there a relationship between alcohol consumption and GPA? All right, which one of those affects which? Well, I guess it could go either way, kind of, but let's hypothesize that my independent variable is the number of drinks per week. The thing that is affecting the other thing is going to be alcohol consumption. And let's set our dependent variable to be your cumulative GPA. So I'm hypothesizing that how much you drink in a given week affects your GPA. That's very important because X and Y have to be set appropriately here. It's kind of like the things that you really care about start to change, as the hypothesis test changes. With something like a t-test, you have to be really careful about X1 and X2 and like how you organize the tails of your test in a directional hypothesis. Here, the big concern is properly identifying X and Y. What is the thing that's affecting the other thing? Here, I'm hypothesizing that your drinking behavior influences or impacts your GPA. So knowing that X is alcohol consumption and knowing that Y is GPA, let's assume that B, forget about A and E for a second. I'll get into that at a later point, a later lesson actually. B is the most important part of the equation here. Let's assume that B equals negative 0.07. The fact that that is negative tells me it's a negative correlation. And the fact that it is 0.07 tells me the change in Y given that 1 drink increase per week. So here's how I would interpret that. Once the equation spits out negative 0.07, a 1 unit increase in number of drinks per week is associated with a 0.07 unit decrease in cumulative GPA. Notice how that fixes every weakness that I was dealing with in my correlation problem, because now I can say what is the specific effect of X on Y, in what direction is it going, and what are the units that I'm operating with here. It's actually measured and expressed in the units of the dependent variable, the units of GPA. I think that's amazing. So I'll repeat that. A 1 unit increase in number of drinks per week is associated with a 0.07 unit decrease in cumulative GPA. How do I know it's a decrease? It's negative. So let's just say, for the sake of argument, I had a positive coefficient here. a positive beta value. All that would change is the direction. So assuming a positive coefficient of 0.07, the interpretation would then change to a 1 unit increase in number of drinks per week is associated with a 0.07 unit increase in cumulative GPA. That would be weird, but that's what the numbers would tell you in that case. So pay very close attention to this. A positive coefficient for B denotes a positive correlation, and a negative coefficient denotes a negative correlation. Nothing more complicated than that. This is something that takes time and mental energy to master, but when it clicks, I do think it really clicks. All right, one more example, and then we will move on in our next lesson to actually calculating this. Let's say I have this example. I've been, there's a reason why I've been hitting this example of education and income. Let's say I am hypothesizing that the years of schooling that you have completed is something that influences the amount of money you make. So I'm going to let X equal years of education. That is my predictive or my independent variable, and I will let Y be income, which is my dependent variable. So education affects income. And let's say the B coefficient is calculated here to be 3,700. All right, a 1 unit increase in X is associated with a B unit change in Y. Try your hand at writing down what that interpretation would sound like using that language. A 1 unit change in education, years of education, is associated with a B unit change in income. Okay. Here's how I would do that. A 1 unit increase in years of schooling or years of education is associated with a $3,700 increase in income. It's amazing. There is nothing in this world more important to me than regression. I'm not kidding about that. So regression's big advancement here. We have incorporated the magnitude of the effect, and we have incorporated the unit of expression here. But the magnitude of the effect, what I hope this lesson has shown you, is really all that is the slope of the line. It's the average change in the slope, like the way the line moves. Does it move up? Does it move down? How steep or how mild is that change? That's all you're doing here. That's all you are quantifying is the slope of the line. And this stuff's important. This stuff is really, really important because for sociologists who care about specific effects and sociologists who care about multivariate relationships, this is how it's done. I would estimate that about 75% of all quantitative sociology that is published is using some variation of the regression technique. And there you can throw all sorts of bells and whistles on this. You can, controls, clusters, all that crap. But the general gist of the equation is always the same. What is the effect on the dependent variable given and assuming a change of 1 unit in the independent variable? So I hope that makes sense. Feel free to email me and talk to me if it does not. Otherwise, we're moving, man. We're moving to the end here, and we're learning some really valuable stuff here at this point. Okay, so stick with me, and we'll all get through it. I promise. Math to come the next time we meet. Thank you very much, and goodbye.